Okay, welcome back. We're going to move on from the magnetic effect of the current. So 18.6 magnetic effect of current, we've learned that the relationship between electricity and magnetism, that is whenever there's a current will produce a magnetic field around it, right? And so somehow electricity and magnetism are super related, right? So we're going to move on to how that applies in real life. We've seen one example, the circuit breaker, but really this relationship, the reason why it's so useful is because it's applied in one of the most important things in modern life around us. It is applied in motors, right? So that's why we call it the motor effect. You're not really going to really fully understand how this applies to motor until we reach the end of this chapter, but follow along the story, okay? Then you start to come together. Basically, we're talking about force due to magnetic fields, okay? Force due to magnetic fields. So what we're going to cover is what happens to a current carrying conductor when I place it into an external magnetic field. Okay, what happens then? What happens when I reverse direction of the current and the magnetic field? And then how can I determine the relative direction of these quantities? Okay, so let's watch this video to find out what happens when I place a current carrying conductor in an external magnetic field.
So I have here a large magnet, south pole, north pole, so the field is pointing up. And then I have a big, copper tube, which is connected to the wires here and there. When I connect these here, electricity will flow through this guy, through the red, through the copper tube, and then up through ground, and then back home. So we'll have electricity flowing this way, magnetic field pointing up. We expect a force inward. And sure enough, we get an inward force. Now, if I reverse the direction of the current, we expect an outward force.
Okay, so what you see there is when you put a moving charge, or basically a current carrying conductor, into an external magnetic field, it experiences a force, right? And this idea is going to be super important, right? So this is key idea 2. Key idea 1 is a moving charge or a current will produce a magnetic field around it. And now when you place this into an external magnetic field, it experiences a force. Why do you think this happens? Why do you think this happens? Right, so this is what we're talking about here. This is basically a similar setup to what the guy had in the video. There's a current here. It's a current here in magnetic field. Suddenly this current carrying conductor will experience a force. Okay, and this effect is called the motor effect. Why does it experience a force? Well, we already know that a current carrying conductor will have its own magnetic field, right? This magnetic field is the magnetic field due to the current in the wire, right? So this current carrying conductor has its own magnetic field. In this case, it's this way, right? If I put it into a magnetic field between two magnetic poles, right? This is an external magnetic field. I take some liberties in emphasizing the word external here. So it's an external magnetic field. I take this and I put it in an external magnetic field. You see that, hey, I have two magnetic fields now. One from the wire itself, that will always be here because it's because of the current that there's this magnetic field. And I put it in an external magnetic field. The magnetic fields are going to interact. They're going to interact in such a way where it's going to repel almost, right? Repel the wire or the current carrying conductor away in this direction. Okay, why exactly, you don't really need to know. But basically, we look like these are all the bunched up on this side, because on this side, you see this is a clockwise field, right? On this side, it adds to each other. On this side, it kind of cancels each other out. So there's a weaker magnetic field here, a stronger magnetic field here, and basically, for some reason, this interaction results in a force that pushes it outwards. Okay, in this direction. So, what do you think happens when we reverse the direction of the current?
So I have here a large magnet south through the, we expect a force. Direction of the current, we word force. Now, if I reverse the direction of the current, we expect an outward force. Get this guy out of the way.
Okay, so you see that the force goes in the opposite direction.
And there you see it, floating there. Because now that I've reversed the direction of the word force.
And that makes sense, right? That makes sense, right? Why does it make sense? Because if I were to go back here, if I reverse the direction of the current, this field's direction is also reversed. So you'll see that the effect is going to be the opposite, because instead of a clockwise field, it's going to be an anti-clockwise field. This side's going to be stronger, this side's going to be weaker, it's going to go the other way, right? So is there a way for us to identify the direction quickly? Yes, there is, and that's key idea 3. The direction of the force is hence related to the direction of the current and the external magnetic field. Okay, so I'm telling you the direction of the force is related to the direction of the current and the external magnetic field. Why? Because you need to understand why the force happens in the first place, right? The force happens because the current produces a magnetic field. This magnetic field interacts with the external magnetic field, which results in a force. So the direction of the current will result in the direction of the current and the direction of the external magnetic field. These things determine the direction of the force. And how are they related? They're related. You can find out the directions with a shortcut method using the Fleming left-hand rule. So what is the Fleming left-hand rule? If you notice, let's say this is the direction of the current, this is the direction of the magnetic field, of the external magnetic field. Okay, so red color is the direction of the external magnetic field, blue is the direction of the current, and then the force is represented by this green line. If you use the Fleming's left-hand rule, now it's left. So just now you only learned right-hand grip rule, Fleming left-hand rule. Okay, right-hand grip rule, Fleming left-hand rule. So Fleming left-hand rule, basically you point out like a gun first, and then you lift up your middle finger, pointing diagonal. Okay, so note that all three are diagonal to each, not diagonal. All three are perpendicular to each other. Okay, so perpendicular, perpendicular. Okay, just like the picture there. Okay, perpendicular, perpendicular. Okay, let each represent a different thing. In your textbook, it tells you to use motion, field, current. I think that's very, but it's not actually motion, right? It's actually force. So I don't really like it, and I don't think this really helps you to remember better anyway. I think it's probably confusing. So I'm just going to change it to force, field, current. I don't think it's very hard to remember. Force, field, current, just repeat it a few thousand times in your head. Force, field, current, you remember force, field, current. Okay, force, field, current. Anyway, force, field is like a thing, right? You don't play games called force, field. So force, field, right? So force, field, then last one, current now. Okay, so anyway, force, field, current, the thumb is force, field is the second finger, and then current is the middle finger. Okay, force, field, current. Okay, so these are always, the identity of each finger is always fixed. This is always force, this is always field, this is always current. Okay, if you have any two, you just need to align the two, and then you'll find the last one. Okay, so let's say now, for example, right, we have the current. Okay, we know that current is flowing from here. Let's say we don't have the force, we want to find the direction of the force. Okay, let's try this example. Okay, so current is the middle finger, so you point your middle finger in the direction of the current first. Okay, can you do that? Point your middle finger in the direction of the current. Keep your hand like that, in this shape. Point your middle finger in the direction of the current. And then your second finger, your index finger, point to the direction of the field. So the field is going from bottom to top. So your thing should be looking like this. Your finger should be looking like this now. My middle finger is pointing kind of like into the page, because the current is going into the page. This is going up. And where do you see my thumb pointing? So with these two is pointing in the correct direction based on the situation. My thumb is pointing to the right, and that is exactly where the force will be. Okay, so you have any two, you can find the last one. Don't worry, we'll have a bit of practice. Okay, note that the force, current, and magnetic fields are right angles to one another. They are all at right angles to one another. Okay. So direction of the force is hence related. The same thing I said just now. So let's try this now. For this scenario, if the current is flowing from A to B to C to D. So A to B to C to D. The wire will swing in what direction? Okay, use your left hand, Fleming's left hand rule. Okay, Fleming's left hand rule. Current, field, force. So the force is right, so the thing will move outwards. Okay, what happens when I reverse the current? So now current, if current goes from D to C to B to A. So current now is going in this direction. Okay, current now is going in this direction. If current is now going in this direction, my previous hand is here, my field is still pointing upwards, so my index finger is still pointing upwards, but my current is no longer going into the page, it's flipped to this side. Okay, you see the current is now pointing, force, field, current is pointing towards myself, right? And look what happened to my force, right? My force gets flipped, and now the force will be to the left, and so the wire will swing inwards. Okay, the wire will swing inwards in this direction. Okay, this will be the force. Okay, so the direction of the force on a current carrying conductor is reversed when we reverse the direction of the current. You get it? So if I reverse the direction of the current, the direction of the force will reverse. Why? Because force, field, current, if you just take your hand like that, and just flip up, right? The current flip side, my force also flip side. Okay, the current flip side, my force also flip side. Okay, current flip side, force also flip side. Okay. So for current flowing in the direction, so let's do another example now. What if, so let's have the current flowing from A, B, C, D, so as according to this diagram, but instead, what if the direction of the magnetic field was reversed? So just now north to south, now I flip it, north on top, south below, means my field is which direction? My field is now going downwards, so this is my field, magnetic field. Force, field, current. Okay, I want to find the direction of the force. My current is into the page, my field is downwards, so my force will be towards the force, field, current. Sorry, wrong. Force, field. This one is the field, right? Force, field, current. Field is downwards. Current, okay, current is force, field, current. Current is into the paper. Field is downwards. So my force is to the left. Okay? Force, field, current. Current is into the paper. Field is downwards. Force is to the left. Okay? In the exam, your piece of paper can move. You don't have to twist your hand until your hand break. Okay? Just move the paper. But if I move the paper, now the camera also moves, so very confusing. That's why I'm twisting my hand. Okay? But in reality, you can always move the paper. Okay? Yeah. So, the direction of the current, the direction of the force on the current carrying conductor is reversed when we reverse the direction of the current, which we saw just now, and now magnetic field. Okay? So if either the current or magnetic field, the direction is reversed, the force also will reverse. Okay? But basically, you just always use a Fleming left hand rule correct already. Okay? But yeah, intuitively, something that if you do enough practice, you'll know lah. If one thing flip, right, the current flip, the force will flip. If the magnetic field flip, the force also will flip. So any of those flip, the force will flip. Okay? Okay, so let's go and try handout 2, question